All right, good morning, everyone. So now we get to actually talk about virtual memory now. So hopefully you kind of know, I guess, what's going on, but this is actually where we'll talk about the translation and actually know what the MMU does, which we won't learn today. So today we'll be talking about single level page tables, and page tables are what does virtual address to physical address translation. So remember, virtualization is like just the concept of fooling something into thinking it has all the resources. So both, if we had LibreOffice and Firefox, if they both use virtual addresses, they would think they have access to everything, and then the kernel is free to map it to physical memory and give or not give physical memory to each process as it sees fit. So if we want to implement or use virtual memory ourselves, we'll probably have this checklist in mind where if we have virtual memory, we want multiple processes to be able to coexist, and they should not be aware that they're actually sharing physical memory if the kernel decides that's an optimization it would want to do. So one optimization would be that it would only load, for example, libc into memory once, and then every single program that uses libc could actually just have access to the same physical memory where it would just execute code from, and each process should be none the wiser. And if it needs to be independent, the kernel has to make sure that it does actually have an independent view of memory. So we also want processes to not be able to access each other's data unless you explicitly allow it. So there is a mechanism where we can share memory between processes in order to do some communication, but you should have to opt into that. By default, everything should be completely independent. And then, of course, you want performance as close to possible as using physical memory with virtual memory. If it is twice as slow, you probably don't want to use it and would rather have the headache of using physical memory if it's going to be something like twice as fast or 10 times as fast. So we want performance as close as possible. And then we want to limit the amount of fragmentation, which is a new keyword that we'll be going into, especially when we talk about memory allocation. And fragmentation is basically just wasted space. So memory that should be usable, but for some reason is not usable. Oh, we do talk about that. So we'll actually, I thought we were going to talk about it later. All right, so now we get to be introduced to the MMU, or the Memory Management Unit. And all it does is map virtual addresses to physical addresses, and also does some permission checking. For example, maybe there are some addresses that you should not be allowed to write to, so it would have permissions for that. So the prevailing technique that is actually still used today, it's been used since the 70s, is to divide memory up into fixed size pages. So typically these are 4,096 bytes, and that is the page size of your actual machine now in all likelihood. So the reason of doing this is because they don't want to translate every single address byte for byte. You would want to group them somehow. So they just picked this as a big group size in the 70s, and for some reason it still works pretty well today. So when we divide these memory up into fixed size pages, the terminology is a bit different, whether you're talking about physical memory or virtual memory. So a page in virtual memory is just called a page, nice and simple. In physical memory, sometimes it's called a frame, sometimes it's called a physical page, and all sorts of kind of different terminology. But usually when you say page, that means virtual, a fixed size page in virtual memory, and sometimes you might refer to physical memory ones as also a page, but technically most people refer to it as a frame. So one really old technique is to divide memory up into segments, or into segments. So you divide the virtual memory space into segments for memory with different permissions. So you would organize it into code, which would be memory you're allowed to read and execute. Data, which is memory you maybe just be allowed to read, maybe allowed to write. And then stack, which would be read, write, and then the heap, which would be rewrite, but located somewhere else in memory. So this kind of looks like an ELF file where there's large sections of memories with permissions. And then each segment is a variable size, and you can resize them dynamically. But this is like a really old legacy thing that's not really used anymore. And segments are really costly to relocate to, and can lead to a lot of fragmentation if you run out of memory, or like your code and data are right next to each other. So if you want more memory for the code, well, you have to move all the data, copy it all, shift it over, and then you're allowed to grow your code. It's kind of bad in that way. It's no longer used, but the terminology still exists because this is where the term segmentation fault comes from. So even though we don't use segments anymore, we still get seg faults because that was the name they were using before. Oops. So a little bit more details, even though it's mostly irrelevant. Sometimes it's still covered in courses. So each segment is pretty simple. It contains a base address, a limit or a size, and then permissions. So how you get a physical address is you use a segment selector because there's only typically like 4 of them, and then an offset where in that segment you want to be. So the MMU is going to check that the address you're accessing, is valid, so it's within the size limit, and then to calculate the virtual address, it would just look up that segment, add the base address of that segment to that offset, and do the permission checks, and then otherwise if it doesn't line up, or if you have the wrong permission, segmentation fault. So for example, if you use something like this as an address, 0, 1, and then segment selector, you want to use FF. So somewhere there would be segment 1, and for example, it would have the base of address 2000, have a limit of 1 FF. So to do the translation, it would be FF, and then the limit is 1 FF, so it's within the limit, so that's fine. And then it would just add the base address to that offset. So the physical address for segment 1 FF would be 20 FF. So it just adds them together, kind of like we've dealt with pointers all the time, so this should be pretty much similar. So on x86, these segment selectors do exist and are still used by the hardware because they have to be backwards compatible, but Linux just cheats and says the base of every one of them is 0 and the limit is the maximum amount of your memory. So if you use a segment selector or do anything weird, you'll just get the exact you'll get the exact physical address as you're looking for. So it pretty much negates the whole system. So if you're on x86, that's what will happen. Okay, so nowadays we have 64-bit machines. Typically you don't need to use all of them because 64 bits, if they're all can each point to a byte, is a lot of bytes. It's like what, like 16 exabytes or something like that. So you actually don't need to use all that memory yet. Maybe we'll get there in 30 years. Well, probably not even that. But we're not going to use them all, so we can use them all for some different purposes. So CPUs have different kind of levels of virtual addresses you can use. The implementation ideas are all the same. So for now, we'll assume only 39-bit virtual memory addresses, and that's used by RISC-V, it's used by ARM, it's used by, I think you can do it on x86 as well. So we'll just assume that it is like a pretty realistic one that's also not overly complicated. So if we have a 39-bit address, that means we have 512 gigabytes of accessible memory, And this scheme of having 32 or 39-bit virtual addresses is sometimes called SV39. And at its most basic, it's just a lookup table. So it's implemented with a page table. It's indexed by the virtual page number, which is the virtual addresses that the application would use, and then it would look up the physical page number. So let's look at an example. And this is exactly what it would look like. So at the top there in the blue is a virtual address. So if we have a page size of 4096, that means we have 12 bits to describe our page, because 2 to the power of 12 is 4096. So that's our offset into the page, and we're doing translation about the page. So this offset into the page, we don't have to touch when we do any translation. So it's where in the page you are. You don't have to translate that part. It's exactly the same in the physical address. And then all we're doing is translating the virtual page number to a physical page number. So if we have 39 bits of virtual address space and our page is like 496, we would have 39 minus 12 bits left for our virtual addresses. So that's why it's 27. And then since we have 64 bits, we have 25 leftover bits that can be used for future extensions. So using this index, so it would use this virtual page number, look it up in a page table, and this would be used as an index. So this page table would have 2 to the 27 entries, and each entry would just store a page number. And because we don't have to translate the offset, we essentially have 12 bits we can use for storing other information about pages. So they set aside 10 of those bits to use for flags like permission checks and all that we'll see shortly. So that's actually what's in a page table. So any questions about this? Okay, so it's just a lookup table, not too hard yet. So let's look at how the translation would actually happen. So if we consider the page table up here, so it is virtual page numbers in the first column, so 0, 1, 2, 3, and then the physical page numbers, which would be like 1, 4, 3, 7. Then we would get these following translations, and we'll go through them quick. Yeah, so there's a question, so does the index and the virtual address, the 27 bits, which point to the index of the virtual table, which contains information of the physical page number used in the physical address, while the offset is exactly the same. Yeah, so we don't translate the offset because it's within a page. So we're just translating pages. So a virtual page to a physical page, so we can actually look it up in memory. Okay, whoops. And yeah, the flags would be something for, we'll see what the flags are for later. But if this is our page table up here, then we can do the following translations. So we'll assume our page table size is still the 4096 bytes. So that means each hex represents four bits. So we don't have to translate the last 3 numbers because they're the offset. So this would be the offset into our page, would be AB0. And then, so this is our offset. And then this would be our index into the virtual, this would be the index of our virtual page that we need to look up to get a physical page. So 0 is just, if we look it up, it translates to 0x, or sorry, yeah, 0, 1, sorry. So that would be our physical address. And then what would this address translate to? 1FA0. Yeah. 0x4FA0. Yep. So these are questions you would have. That's just really basic translation. So this address 2884, well, 2 is our index. So if we look up 2, it corresponds to the physical page number 3. So it would be 3884. Oops, my writing is terrible. This should be a 3. So if we have 32D0, then that would translate to 0x7 2D0. Any questions about that? So our page tables are pretty much just a simple lookup table, and that's the trick. Okay, well, let's go into another type of question we might encounter. So assume that you have a 8-bit virtual address, so we'll just make it really, really small, just so the numbers are a bit more easier to work with. So you have an 8-bit virtual address, you have a 10-bit physical address, and then each page now is 64 bytes. So these are questions you should be able to answer. It's like, how many virtual pages are there? How many physical pages are there? How many entries are there in the page table? And then given a page table, do the translation. So anyone for the first one? So how many virtual pages might there be? To the 8? Yeah. So to the 8 is the number of, that's like the bytes range of our entire virtual address. Yeah. Yeah, so it is, 2 to the 8 divided by 2 to the 6, which is the 64. So that's 2 to the 2, which is 4. So there are going to be 4 virtual pages. What about physical pages? Sorry? $64? $16? 16 seems reasonable, yeah. Everyone agree with 16? So the total range of our physical address space is 2 to the 10, and we have 64 byte pages, so divided by 2 to the 6. We know our little tricks, right, with exponents. So it's just 10 minus 4, so it's 2 to the 4, which everyone should know because we're computer engineers, so that's 16. So if you just divide them, 16, so there's more physical pages than virtual pages, which makes sense because there's 10 bits for physical addresses and there's only 8 bits for virtual addresses. Then how many entries are in the page table? Well, it's just however many virtual pages there are. So it's 4, and also that there's a page table right below it, so you can count 4. So in this page table, it's just in order of indexes, just as an easier way to write this. So virtual index 0 would be this, would be 02. Virtual index 1 would be 05. Virtual index 2 would be 01. And index 3 would be 08. So what is the physical address of F1? Well, we can just write out the binary and just do that instead. So this is, remember this is our virtual address. So our virtual address would be, if we write that out, F is 1, 1, 1, 1, and 1 is just 0, 0, 0, 1. So remember, we said that each page is 64 bytes, so our offset is going to be the lowest 6 bits. So this is our offset. So that would stay the same. So we'll just write in binary because this is a bit easier. And then 1, 1 is our index. What is 1, 1? 3. So it would correspond to this entry here. It would be the last entry in the page table. So if we just translate that, and 8 is 0, 0, 0, 1. So if we convert this whole thing back to back to hex, it would be 1, then this is 3, and this is 2. So our address at the end of it would be 231. All right, any questions about that? Because yeah, we're going to have a fairly easy day today then. So there's no questions about that? Yeah. Oh, yeah, so the question, how do I get the offset to be 6? So in the question, it'll say what the size of the page, what the size of a page is. So this is a 64 byte page, and 64 is just 2 to the 6. So the lower 6 bits is going to be the offset there. So it's within the page. Yep. Yeah, so which would range between 0 to 63 to get you there. So that's why if we have a 4096 page size, that it's 12 bits. Okay, so there's all our answers we came up with. No problem so far. So this is actually what page table entries look like. So if you want to explore the flags a little bit more. So in this case, there's the physical page number, which is 43 bytes. So it uses 56-bit physical addresses, and these are all the flags. So there's one flag that just says whether or not this translation is valid, because that's something we might need if you're the kernel later, if you want to invalidate ones. And then there's a read flag, write flag, execute flag, and then other flags we don't have to worry about, like is this user memory, is it global memory, has this been accessed before, and then a dirty bit, which we'll see later when we talk about what to do when you actually run out of physical memory. So one thing you can do is just swap it all to the disk and fake that you have lots of memory when you actually don't, which is another benefit of having virtual memory, but we're not going to talk about that until probably like next week. So the MMU is the hardware that does the translation, and it also checks these flags. So for the purposes of this course, we'll just focus on the first 5 flags. So whether it's valid, readable, writable, executable, and a user flag, so the kernel can figure out, hey, is this address, or is this physical page used for a user process, or can I monkey around with it? Oh, there's a question about, got confused by the bit conversions. Why is dividing them giving us the number of pages? So if we go here, so the number of virtual pages, so because we have an 8-bit virtual address, that means we can address 2 to the 8 bytes. So that's where our 2 to the 8 number comes from. And then if each page is 64 bytes, you would divide it up to get the number of pages. So the total number, or the total memory you could address divided by the number of pages is the number of, or sorry, by the page size is the number of pages you'd have to represent all of memory. So that's why we do the entire address range, which is 2 to the 8, divided by the page size, which is 2 to the 6. Yep. Sorry, this? Oh, this? Yeah, so the 2 in the final answer. So that just came from translating it. So this was our virtual address when I wrote out. This was F, and then this was 1. So here, I'll translate it again. So for the last 6 bits, I don't touch them because they're the offset. So the last 6 bits, when I translate, I don't touch them because they are the offset. So it would look like this. And then for translating the virtual page to the physical page, it would be index 3 here, because it's 3. So if I look it up, it translates to 8. If I write out 8 in just binary, it would be 1, 0, 0, 0. So I have to put that at the front of this. So if I do that, it translates to this, which is now a 10-bit number instead of 8-bit. So if I want to bring it back to hex, I have to group them into 4s. So I group them into 4s, and then this would be a 1, this would be a 3, and this would be a 2. Yeah, and this is just uber annoying because the page size doesn't nicely line up to a hex size. So usually you do, just to make it easier to write and just for convenience, they're usually, dividable by 2 to the 4, just to make your life easier. But this is like exceptionally kind of mean and tedious. But that's as hard as it would, but that's as hard as it gets. Yeah, so we'll just focus on the first 5 flags. We're actually not going to be implementing them or doing anything with that. But we should kind of understand what the flags are and how the kernel could use them to its advantage. So this is the address space for each process, and each process we know gets its own address space. So this is kind of what it looks like. If you look at like very simple operating systems, like there's XV6, which is like MIT's small Unix kernel. It looks like this. So at address 0, it puts all the user text and data. Text is just a weird word. It actually means code. So it's actually information you can execute. So it just throws it all there at the bottom, and that's what would be loaded in from the ELF file. So that's all your addresses, all your global variables, all of that would just be mapped to some lower region of virtual memory. And then above that would be the user stack, which would be like on pthreads, it's like 8 megabytes. And then above that would be the heap that typically starts at the top and then grows down. And then for this really simple operating system, there's a trap frame and a trampoline. We don't have to know that, but that's basically mechanisms that it uses to switch between kernel mode and user mode. So the trap frame would store all the registers and everything whenever you initiate the switch from user mode to kernel mode, and the trampoline is just some way of actually changing modes where, if the kernel is changing modes, it has to change to its address space, and it might need to access something from the user process, which it can only get by being in the user address space. So that's all stuff beyond the scope of this course that's mostly for monkeying with that transition. So each process gets its own page table, and that's how we make address spaces. Just each process gets its own page table, that's it. So whenever you fork a process, now we understand a little bit why it could be much slower. Is when we said it was an exact copy, we didn't lie. So it would copy the page table from the parent. So that's why everything maps up to be exactly the same, but separate. So if you didn't have any optimizations or anything, whenever you copy the page table, you would also have to copy the pages into new physical memory if you wanted to make a complete copy of it, but that would be pretty slow. So one optimization the kernel has that's really important is something called copy on write. So what that will do is whenever you fork, it will copy the page table and then turn off the write bit on all of the addresses. So you can, both of them can read to them and they'll read to the same physical address. But as soon as one starts to write to it, it will generate a page fault in the kernel, which means, hey, you're accessing it in a way you shouldn't. And then only at that point, the kernel can be smart and actually physically copy that page to another physical address and then do the modification and then make it writable in both. So you have really fast forking and it still has that illusion of everything being separate. So finally, we've talked about it now. So there is a very big problem with these page tables though. So the page table we were talking about before, if it is a 39-bit virtual addresses with 4096 size pages, that means that if we have our page table, it is 2 to the 27 entries long. And each of the entries in the page table is going to be 8 bytes. So if you multiply those two numbers together, it means each page table is 1 gigabyte. So if one page table was 1 gigabyte in your machine, how many processes could you have? Like 8, and then half of the memory is probably in page tables. So there's something going on here because that doesn't quite make sense. But we have processes, we have lots of processes on our machine, and they can access up to 8 gigs of memory without this whole thing. And when you start off some little console application that barely uses any memory, it doesn't use a gigabyte of memory. So something's going on here. So again, talking about the RISC-V translation, it is a 39-bit virtual address to a 56-bit physical address. So 10 bits to spare in the physical, in the page table entry. That's what PTE is. And they could expand it. It's all future use. And for the purposes of this course, and for the purposes of pretty much any hardware you'll ever see, that's the page table size, 4096. And that's why I kept allocating buffers in that size, because the kernel only cares about pages, and that's kind of the default unit of memory it deals with is pages. Yep. Can you? Yeah, so the question is, can you manually change the page size? Because, this was in the 70s. What about if we just increased our page size to, the next factor of 4 up or something like that? So there is something you can do for that. They're called huge pages. So there's actually a push now that with really, really memory intensive applications, some hardware will let you use 2 megabyte pages, and then some will go up to, I believe they're gigabyte pages. So that makes translating really easy if it's just a gigabyte page. So there's not much you have to do. But there's going to be some trade-offs. So if that's our page size, then our application has to use at least 1 page, and then every application uses at least a gigabyte of memory. So 2 megabyte, though, is probably actually more realistic nowadays. But that's an option you can do on newer hardware. But the default is still going to be, from the 70s, it's still going to be that 4096. Oh, whoops, I didn't fix this. So you may be thinking this seems like a lot of work. So this is actually in lab 4, you'll be doing a fork followed by an exec. I did not update this, my bad. So if you do a fork followed by an exec, one of the questions you might have, so exec will also create a new address space for the new process. So it seemed kind of wasteful that we would copy all the page tables and possibly copying memory when we're just going to exec anyways and blow it up. So there's actually, the developers actually thought of that, and there is another version of fork. So there's a system called vfork, which by default shares all the memory with the parent. And it is then undefined behavior to actually modify any memory in the child. So the only purpose of it is to immediately exec, and you're not allowed to do anything else. But this was only really used for really performance-sensitive applications. So any questions for anything with today? Because I'll leave it off on the super hard note. Okay, so single level page tables, really bad because they would be, at least with this scheme, it would be gigabyte sized page tables. So obviously they are not a thing. So what you actually do is do something called a multi-level page table. And that saves space for applications that just don't have very many applications, or don't have very memory, that don't use very much memory. So the idea here is to divide up our page tables into a series of smaller page tables that kind of cascade with each other. So if we take our if our page table size is 2 to the 12, and each of the entries are 8 bytes, which would be 2 to the 3, the idea here is to make each of the smaller tables exactly fit on a page. So if they're each 8 bytes, that would mean I can fit 2 to the 9 of them. So in here, all of our pages, or all of our page tables would fit on a page, so we would have 2 to the 9 entries in them. Everyone follow, hopefully. So then, to do multi-level page tables, I would divide up that 27 bytes that I originally used as an index into 3 of them that each represent a different level. So the highest level page table here, the level 2 page table, well, when it goes and looks up into it, it would look up the index, so it would be, 0 to 2 to the 9 minus 1. And for the physical page number there, instead of doing that in the translation, that would actually correspond to the level 1 page table. So we would follow that to the level 1 page table, and then use the index from the virtual address here, and then that would correspond to another page table. So that would correspond to the level 0 page table. And then in the level 0 page table, the lowest level page table is going to act exactly like our single level page table, where we just find the physical page number and use that in the translation. So we go through multiple levels here, and then at the last level, we just do the same translation we always do. So the offset stays the same, and then the physical page number is whatever we looked up in the lowest level. And that's okay if it doesn't make sense, because this is just a preview for next lecture. So any questions about single level page tables now, though? They're big, wasteful, but they're just big lookup tables. They're just a big table. All right, cool. We get a bit of a break and we get to end early. So, pulling for you. We're on this together.